Thanks for watching AI Weekly Update from Henry AI Labs. This week we'll start with the Plan to Explore algorithm, an interesting approach to exploration and reinforcement learning by using a world model to predict novel states based on the uncertainty between an ensemble of predicting the next state given a state-action pair. Then we'll look at movement pruning, adaptive sparsity by fine-tuning, a new paper from researchers at HuggingFace that look at how we're going to prune networks that are being fine-tuned from, say, being trained on this pre-trained language modeling task down into tasks like text classification, named entity recognition, or question answering. Movement pruning shows that it's better to use first-order information about the weights rather than absolute value magnitude pruning for achieving sparsity with these fine-tuned networks. Then we'll look at data augmentation for NLP, a really great visualization of what's been tried to augment datasets for natural language processing. Then we'll look at NVIDIA's Ampere architecture and the A100 GPU, particularly claims about how they're speeding up sparsity with respect to running the forward passes of these models. They also released two interesting research projects, MegatronBERT, which scales BERT up to 3.9 billion parameters using the Megatron model parallelism technique, and Flowtron, a flow-based generative model for doing text-to-speech synthesis that has some really interesting properties, especially with controlling the output with respect to tone and style and interpolating between samples. This week, Google's AI blog described the data echoing technique, a technique to avoid GPU idling by reusing old batches of data while waiting for the CPU processes to give the GPU or the TPU a new batch of fresh data. Then we'll look at ESPRIT from Salesforce, a technique to explain solutions to physical reasoning tasks on the PHYRE benchmark, where you have to place a red ball that knocks into the green ball into the blue ball. So they're looking at ways to interpret how these models are reasoning about the physics in this simulated environment. Then we'll look at Meta-Dataset, a new dataset from researchers at Google that explores the current state of few-shot learning models on a very diverse dataset. So usually these few-shot learning models are evaluated on Omniglot or Mini ImageNet, where the real visual domain isn't varying as much as the diversity in this meta-dataset. Moral, model-based offline reinforcement learning, describes a technique using a pessimistic MDP and an unknown state action detector to utilize model-based reinforcement learning from offline data. Bayesian Bits describes a technique to combinatorially explore different quantization bit widths on different layers of the network. Prototypical contrastive learning is a similar approach as supervised contrastive learning, where you use the embeddings of nearby prototypes to have the classification of the positive key and the dissimilar keys in contrastive learning. Rather than just using a data augmentation view of the same image, you use the distance to the other images in the prototype. Microsoft has also released a new vision language transformer model, Oscar. In this model, they're using more text information from the image features to better align the vision and language information. Facebook has also announced the Hateful Memes Challenge, a dataset containing about 10,000 of these memes, and it has an $100,000 prize and is going to be listed at the NeurIPS 2020 competition track. Then we'll look at some really great articles from HuggingFace and Weights and Biases, such as the integration of weights and biases with HuggingFace models, and a really easy example showing how to use the weights and biases interface to visualize fine-tuning BERT on the Microsoft Research Paraphrase corpus in HuggingFace. Then we'll look at the new NLP library, containing about 100 datasets and 10 evaluation metrics for natural language processing, released by HuggingFace as well. From Weights and Biases are two really interesting articles about natural language processing, the first of which describes how to fine-tune GPT-2 with reinforcement learning and proximal policy optimization to control the output of the text to have a positive sentiment. Also from Weights and Biases, we'll look at this visualization of hyperparameter tuning between BERT and DistilBERT, exploring how different learning rate configurations or batch sizes leads to different performance. Finally, in this weekly update, we'll look at an intro to BERT with HuggingFace and PyTorch, one of the greatest tutorials for getting started with BERT, with HuggingFace and PyTorch, and downstream tasks like text classification, named entity recognition, and question answering. And finally, we'll look at an interview between Sayak Paul and Colin Raffel about conducting machine learning research. If you haven't already, please check out this week's episode of Machine Learning Street Talk, where we take apart Yoshua Bengio's second half of the ICLR 2020 keynote, including really interesting topics like consciousness and machine learning, System 1 and System 2 thinking, sparse factor graphs and causality, and many more. Plan to Explore is the latest algorithm to improve exploration in reinforcement learning. Model-based reinforcement learning algorithms learn the transitions of the environment. Sometimes these models are also referred to as world models. In a pixel space world model, you'd be able to input a state action pair and get the next state in pixels. Plan to Explore is a model-based technique, but rather than reconstructing the entire pixel state of the next state, it predicts the future in a compressed, latent space. This technique dramatically reduces the computational requirements of this and has been used in other techniques such as Dreamer or mu0. The novelty of Plan to Explore is that it uses its world model to search for novel states. This is done in a similar way as self-supervised exploration via disagreement, where the uncertainty of an ensemble of predictions is used as the signal for novelty. So if multiple transition models predict very different transitions for a state-action pair, the agent in the real environment will visit it in order to improve its world model and seek novelty. This is a significant distinction between most exploration approaches that calculate novelty retrospectively. This approach seeks out novelty, rather than evaluating novelty based on what it's already run into. Model-based reinforcement learning is very exciting due to its sample efficiency capability. The Cheetah Run environment in DeepMind Control Suite illustrates this well. The world model is trained with this Plan to Explore approach, and then it can be fine-tuned quickly to rewards and tasks like running forwards, backwards, or doing flips forwards or backwards. This plot shows how much better this approach is to training with Dreamer directly with these rewards compared to the quick adaptation enabled with Plan to Explore. This quick adaptation to a new reward is very exciting for robotic control and other reinforcement learning problems. I highly recommend checking out Yannick Kilcher's explanation of this, as well as a Twitter response thread from one of the authors addressing Yannick's concerns about the paper. Exploration has been a booming area of research lately. If you're interested in this, I also recommend checking out meta-learning curiosity algorithms, Never Give Up, Go Explore, and random network distillation. The world model design and Plan to Explore is very interesting as well. If you want to understand this model, read Learning Latent Dynamics for Planning from Pixels. This paper introduces the recurrent state space model, which is used in the Dreamer algorithm as well. Nobody understands fine-tuning language models better than the researchers at HuggingFace, and fewer ideas are hotter in deep learning than pruning, also referred to as sparsity. The most common technique for pruning is to iteratively mask out low magnitude weights. So K% of the lowest magnitude weights are selected at each iteration to be masked out. Movement pruning, adaptive sparsity by fine-tuning, makes the key insight that scoring weights by their magnitude doesn't transfer well to the setting of fine-tuning pre-trained self-supervised models and then fine-tuning them for tasks like text classification or question answering. The authors show that a better technique is to score weights to be pruned based on their first-order movement. First order just describing the change in magnitude rather than the magnitude itself. At high sparsity levels such as 10 and 3%, these models barely lose accuracy on natural language inference and Cora question pair similarity. The loss in the Stanford question answering dataset is pretty significant, although they show that stacking knowledge distillation with movement pruning recovers most of this performance, even at the 3% sparsity level. This is a really exciting algorithm for natural language processing, especially as we are seeing new hardware options such as NVIDIA's A100 GPU that can take better advantage of sparsity. So typically sparsity really only helps for memory reduction, but future generations of hardware accelerators are going to be able to accelerate the time of a forward pass of these sparse networks that have been pruned. While data augmentation is one of the core components of computer vision pipelines, it isn't quite as useful in natural language processing yet. This is mostly because it's hard to define semantically invariant transformations in language. An example of this in computer vision is that horizontally flipping doesn't preserve the labels of MNIST digits. This survey covers many of the techniques that are used in NLP for data augmentation, starting with the most obvious solution of replacing words like awesome with amazing, and then going into a bit of a more complicated way of replacing words with their nearest neighbors in the embedding space, a technique that might be a headache to use with byte pair encoding or subword tokenizations. Most of these techniques are kind of hacky. What I find the most promising is the random noise injection, particularly the QWERTY keyboard error injection. Because when we have these massive data sets scraped from the web, it's not like they're being spell checked before beginning the self-supervised pre-training, and it's likely that maybe some of these keyboard errors could be manifested in the self-supervised language modeling task. I also think mix-up for text could be interesting, where we just scramble sentences together and aggregate the label based on the mixing. At least as a data space regularization technique, this could add some value. Overall, I think this is a really great introduction to what is being tried with data augmentation on text. Similar to applications such as medical image analysis and vision, a lot of NLP tasks suffer from limited data, and data augmentation is one of the most powerful tools for overcoming this in computer vision and maybe in NLP as well. NVIDIA recently announced the new NVIDIA A100 GPU and the new NVIDIA Ampere GPU architecture at GTC 2020. Without getting into the actual details of what is different in the architecture, this blog post reports some massive accelerations with this GPU compared to the V100. In the next section, we'll look at the MegatronBERT, which reports massive accelerations when trained on the A100 compared to the V100. The blog post details massive accelerations with the new TensorFlow 32-bit data type, TF32, Tensor Core operation running 10 times faster than V100 FP32, as well as gains with the bfloat mixed precision Tensor Core operation. If you're unfamiliar with mixed precision training, I highly recommend checking out this video I made going through the Keras documentation for mixed precision training. From a high level, you can dramatically speed up your training with a very small loss in accuracy with about 2 lines of code. I think the most exciting area of the A100 announcement is the accommodation to sparsity. Sparsity describes these neural networks that have been pruned such that most of the weights are set to 0 with the use of mass. The A100 has Tensor Core operations to better handle sparsity, claiming 20x gains comparing the NVIDIA V100 FP32 to NVIDIA A100 Tensor Core TF32 with sparsity. Following the announcement of the A100, NVIDIA researchers unveiled 2 exciting research projects, MegatronBERT and Flowtron. MegatronBERT is the world's largest BERT model at 3.9 billion parameters, 12 times the size of BERT large. Scaling up BERT shows continued improvements on tasks like natural language inference, question similarity, and question answering. The blog post shows the massive gains of the A100 GPU compared to V100 for time per iteration with the 3.9 billion parameter BERT model and the 8.3 billion parameter GPT-2 previously explored in the Megatron paper. Megatron is the system NVIDIA has developed to enable model parallelism. The article describes that with the 32 gigabyte V100 GPU, you can only fit a 1.2 billion parameter GPT model on that chip, so they have to split the model across GPUs. This technique is known as model parallelism. The authors also cite the importance of rearranging the layer normalization to scale BERT up to this size. NVIDIA also released Flowtron, a new autoregressive flow-based text-to-speech synthesis network. You can see a lot of interesting properties of this model in the blog post, such as the ability to control the tone and style and interpolate between samples. This model is a flow-based generative model, which is an alternative paradigm to things like GANs or VAEs. I don't really understand flow-based models myself, but this tutorial from Lillian Wang on flow-based deep generative models is a great starting roadmap, and I suspect this recent course from MIT OpenCourseware's A 2020 Vision on Linear Algebra would be a sufficient learning resource if you're willing to put the time into understanding these flow-based models. Data echoing is a technique from researchers at Google to avoid GPU idling. Most deep learning pipelines have this sequence of reading data, usually from the network in big data cases like ImageNet or from the disk with smaller datasets, then shuffling the data, applying data augmentation, batching this data, and then running the backprop algorithm to update the network. In this pipeline, only the SGD update takes place on these accelerators like GPUs or TPUs. And so the GPU has to just sit and wait for the CPU to finish doing things like augmentation, batching, or fetching the data from the network. Data echoing is about simply repeating the SGD step with the same batch of data, rather than waiting for fresh data. The authors show that this reduces training time and preserves performance, and the technique works best the earlier you do it. So for example, if you repeat the old data at the batching level, you still get different batches for the SGD update, which adds a little variation, and if you apply data echoing at the augmentation level, you might get completely different batches at each repeat, because these augmentations like rotation or cropping have stochastic parameters. The gains you'll see using data echoing is entirely dependent on where the bottleneck is in your pipeline, and it seems to me like this is mostly useful for big data applications like what Google deals with. ESPRIT, explaining solutions to physical reasoning tasks from researchers at Salesforce, is an interesting approach to the PHYRE dataset. PHYRE is a benchmark for physical reasoning introduced by researchers at Facebook, where the agent has to choose where to place a red ball such that it knocks the green ball into the blue ball. ESPRIT is a 2-stage pipeline for explainability, where the model first classifies the most salient frames in the sequence, and then the simulator state of those frames is entered into a table. The algorithm then uses a table-to-text approach to aggregate the information from the table into a description of the sequence, ending with sentences such as, "It continues rolling until it reaches the purple floor on the right." And this is done to see if these models are learning miscellaneous physical characteristics like gravity and friction and these kinds of ideas with the PHYRE benchmark. Meta-Dataset is a new dataset for few-shot learning, where models have to learn a classifier given only a few examples from each class. The phrase meta-learning in deep learning literature either describes AutoML, where we're searching through different components like architectures, activations, or optimizers, or meta-learning is used to describe learning from few examples in a task-to-task kind of way or dataset-to-dataset kind of way. This is an example of the latter, where we would hope a classifier can leverage the information from classifying cats versus dogs to transferring to something like birds and horses. This paper describes the state of meta-learners for few-shot classification, such as prototypical networks, matching networks, relation networks, mammal, and proto-mammal. Few-shot learning is usually studied on Omniglot or Mini-ImageNet. Meta-Dataset attempts to transfer across very different visual datasets from Mini-ImageNet and Omniglot to traffic signs, textures, and MS Coco. Their early experiments show that meta-learners are not able to use this dataset better than simply transferring from ImageNet, and different algorithms benefit differently from additional data. Overall, the paper shows that most of these algorithms fail to utilize the diverse datasets and that few-shot learning still has a long way to go. Offline reinforcement learning describes a setting where an agent learns from logged interaction without directly interacting online with the environment. Model-based reinforcement learning describes being able to predict transitions from state action pairs into the next state, or in cases like chess, exactly knowing these transitions. So offline and model-based reinforcement learning can definitely coexist. A model can be learned from the offline data to predict transitions. In this paper, Moral, Model-Based Offline Reinforcement Learning, the authors test this out on DeepMind control suite tasks like Ant, Hopper, Half Cheetah, and Walker. They approach this with a pessimistic MDP. In addition to the learned transition model, they also learn an unknown state action detector that provides a confidence estimate of the model's transition prediction. This is done to combat states the offline data has never seen before, and therefore the transition model has a poor prediction for. This is kind of similar to the plan to explore algorithm mentioned earlier, solely in the sense that there is some measure of ambiguity about transition predictions that's used as a reward signal in plan to explore, and in this case is a proxy to tell the agent that the world model has a bad prediction of this state. Bayesian Bits, unifying quantization and pruning, is a pretty complex algorithm, but there are still some quick nuggets about quantization that can be briefly summarized in this video. Quantization describes reducing the bit width of weights from say 32-bit floats to 8-bit integers. And this is done because it reduces memory storage and also because these tensor core operations run faster with 4 or 8-bit integers compared to the 32-bit floats. Pruning describes masking out certain weights that don't contribute to the network's accuracy, as described when we looked at HuggingFace's movement sparsity paper earlier. In Bayesian Bits, the authors describe that in quantization, the default assumption is that all layers should be quantized to the same bit width. While it has been long understood that low bit width quantization can be achieved by keeping the first and last layers of the network in higher precision. Recent work has shown that carefully selecting the bit width of each tensor can yield a better trade-off between accuracy and complexity. So now we have this AutoML problem again, where we're trying to tune the bit width for each layer, which renders an enormous search problem. Prior to reading this, I fell into the default assumption bucket, although I'm not surprised that this kind of fine-grained tuning would yield some gains, but at face value, my take is that this is kind of squeezing the last drop of juice out of a lemon kind of thing. It's exciting to see further study into model compression, democratizing research and application of deep learning. I didn't have the time to really get into the algorithm, but it's linked in the description of this video if you're interested. I came across prototypical contrastive learning on Twitter, where this table really jumped out. This table makes it seem like prototypical contrastive learning is 20% better than momentum contrast in SimCLR, but a closer look shows that this is a semi-supervised evaluation. Semi-supervised learning describes a setting where there is a little bit of labeled data compared to a larger amount of unlabeled data, and SimCLR and MoCo aren't really well suited for semi-supervised learning, so the comparison isn't really fair. Prototypical contrastive learning, PCL, is a similar approach to the supervised contrastive learning paper recently presented by researchers at MIT and Google. In supervised contrastive learning, instead of using a data augmentation view of the same image as the positive example in contrastive learning, the other members from the classes are used. So you keep cat embeddings similar to other cat embeddings and dissimilar to dogs, but with the noise contrastive loss rather than cross entropy in the label space. PCL uses a similar approach by clustering representations to form prototypes that represent semantic classes. And this is an iterative process alternating between E steps of refining the clustering and M steps of updating the encoder. So it's fairly intuitive that having some labels to see this algorithm with would result in better performance. Researchers at Microsoft and the University of Washington have released a new vision language model named Oscar, Object Semantics Aligned Pre-training. The current approach to vision language models that do things like visual question answering is to extract regions of interest from an object detection model, most commonly the faster RCNN model. These regions of interest are paired with some text describing the image, and then cross-modal attention looks at both the image representations from the regions of interest and the text embeddings. Oscar refines this pipeline by integrating the object tags with the word sequence, since the faster RCNN will also label the region it's describing. The authors show that the semantic space of words is better separated than the image space, so it's useful to integrate additional text information with the regions of interest. This technique achieves state-of-the-art on all tasks with transformer vision language models, particularly making massive gains in image retrieval. Somewhat on the topic of vision language models, Facebook has released the Hateful Memes dataset on harmful multimodal content. I won't comment on the ethics of censorship, but just a quick description of the task and dataset. So this dataset contains 10,000 plus images and comes with an $100,000 prize pool at the NeurIPS 2020 competition track. Examples of this are images of a skunk with the meme text, "Love the way you smell today," or an empty desert with, "Look how many people love you." Two of the hottest companies in deep learning, HuggingFace and Weights and Biases, have teamed up to facilitate visualization of HuggingFace models with the Weights and Biases interface. If you're completely unfamiliar with Weights and Biases, I recommend listening to this interview on This Week in Machine Learning and AI with Lucas Bewald. Deep learning models are unfortunately highly sensitive to their hyperparameters. In the next article, we'll look at the massive performance differences when fine-tuning BERT or DistilBERT based on the setting of learning rate and batch size. Weights and Biases is a GitHub for machine learning models that allows easy visualizations of tweaking these hyperparameters. This quick tutorial shows how easy it is to integrate weights and biases with fine-tuning BERT on the Microsoft Research Paraphrase corpus. Weights and Biases is also becoming one of the best sources of free coding tutorials on the internet. This post looks at hyperparameter tuning between BERT and DistilBERT. The article starts with the motivation behind DistilBERT, having about half the parameters and inference time. Next, it shows how to set up a YAML file to input to the Weights and Biases sweeps tool for visualizing hyperparameter tuning. From the post, you can see how the visualization helps highlight the importance of learning rate versus batch size and finding the optimal combinations of batch size and learning rate for BERT and DistilBERT. Another article from Weights and Biases looks at fine-tuning GPT-2 with reinforcement learning through the proximal policy optimization algorithm. The idea is to seed the language model with a prompt like, "I saw this film at." The language model completes it with something like, "A party and we're excited. The acting is wonderful, the special effects are." And then a sentiment classifier will score how positive the text was, and this is used as the reward signal to update GPT-2 in a reinforcement learning way. This is a very interesting approach to controlling the output of language models presented in OpenAI's Fine-Tuning Language Models from Human Preferences paper. Some other strategies for this include Uber's plug-and-play model, which also uses auxiliary classifiers to steer the language model, and Salesforce's control model, which uses embedding codes to control the output rather than auxiliary classifiers. HuggingFace has also released a new NLP library that provides access to NLP datasets like Squad, Wikitext, and many others as well as evaluation metrics such as BLUE. This notebook shows examples of how to load these datasets and get a quick description of them, sort of like in a pandas.info way. Top-down introduction to BERT with HuggingFace and PyTorch from skok.ai is one of the most straightforward introductions to fine-tuning BERT for things like text classification, named entity recognition, or question answering that I've come across. It shows you how to visualize the tokenizer encodings and BERT outputs, as well as quickly describing how BERT was pre-trained and how to visualize the configuration of the model with the HuggingFace interface. Sayak Paul published an interview with Colin Raffel, research scientist at Google and recently at UNC, who has worked on a lot of interesting work such as the text-to-text transfer transformer T5 model. One recent paper I think is really interesting is how much knowledge can you pack into the parameters of a language model, showing that these language models can perform question answering fairly well without any additional context, solely relying on the weights or connections in the network to store this information, looking like a win for the connectionists. I highly recommend checking out this interview, where Sayak asks Colin about his current research interests, how he chooses research topics, and what motivated the T5 project, and more.